I'm going to work through this related rates problem. We have a 50-foot ladder placed against a large building. So here's our building. Here's our ladder. So it's like leaning up against the building like that. It's 50 feet in length. The base of the ladder here is resting on an oil spill, and it slips away from the building at a rate of 3 feet per minute. So we're going to call this will be, our x-axis, right? And so what they're giving us here is dx by dt, the rate at which it's moving away from this building. So that's just going to be a derivative with respect to time. I mean, ultimately, that's what a derivative is it's a rate of some kind. And they're giving us that this is equal to 3 feet per minute. I'm just going to ignore the units here because it's not important. We're not going to have to change units or anything like that. The units are all going to be consistent regardless. So they want us to find the rate of change of the height of the top ladder, or the top of the ladder above the ground at the instant when the base of the ladder is 30 feet from the base of the building. And so this thing's falling, and so you have movement in the x direction, and then you have this sort of movement in the y direction simultaneously, right? And so they're giving us what that y, or well, they want us to find what that y derivative is when this base here is 30 feet from here. So when x is equal to 30, essentially. And of course, I'm calling the vertical here y. So this is, our y-axis is in this direction like that. And so the first thing to do, I mean, you realize you have a triangle here. And so this will be our y, right? This is x, and then 50. So we have 50 squared is equal to x squared plus y squared, which is the Pythagorean theorem. Let's solve. So we want to find dy by dt. So let's just solve this for y. So y is going to be equal to the square root of 50 squared, whatever that is, minus x squared. Now we're going to differentiate this with respect to time. So we're going to find, we want to find dy by dt. And so first, this is a square root function, and so we have to differentiate y with respect to everything that's under this radicand here. So that's going to be 1 over 2 times the square root of 50 squared, whatever that is, minus x squared. Then we have to differentiate, we have to multiply this by the derivative of what's inside, which is going to be negative 2x times, because remember, x here is ultimately going to be a function of t, right? It has a velocity, right? I mean, it's something that's changing with time. And so we have to apply the chain rule to that as well. So it's kind of like, a function of a function of a function here. And so so this is going to be dx by dt. And so we can clean this up a bit. So dy by dt is equal to negative x over the square root of 50 squared minus x squared. These 2's here canceled, right? And all of this times the derivative of x with respect to t. And now keep in mind that when you take, like when I did this here, this is really plus or minus, y is equal to plus or minus the square root, but because this is, we're interpreting this as a length in this context, we're just going to ignore the negative solution. And so I just wanted to point that out in case anybody tried to object to that. So now pretty much all you do is you just plug in what they get. They give you this dx by dt, that's 3, right? And then they want you to evaluate this when x is equal to 30. And so you just plug in your numbers. Negative 30 over the square root of 50 squared minus 30 squared, all of that times 3. And that's it. I don't feel like putting that into the calculator, but that's what this is what your dy by dt is. That's the rate at which this the top of this is falling downwards at that instant. So this is why they call it the related rate, a related rates problem, right? Because you're given dx by dt and being asked to find dy by dt, so it's a different rate. But there's a relationship between them that you can derive from this Pythagorean identity.